The first few chapters were about putting things together, putting atoms together to make minerals, and putting minerals together to make rocks. With chapter 4, we're taking the opposite approach. We start to break things down. There are two different sets of processes. So weathering and erosion are going to be two of the external processes, things that are happening at or very near the surface of the Earth. We'll talk in later chapters about the internal processes, which are going to be deeper inside the Earth and result in some of the major landforms, such as the mountain ranges that we see on the planet. Your book has three different kinds of external processes that involve breaking apart rock: weathering, erosion, and mass wasting. Now, I've included mass wasting here within erosion, because in my mind, regardless of the method by which the material is being moved, it's still erosion. So your book restricts erosion to movement of material by water, wind, or ice. I include gravity, even though your book would separate out gravity and say everything that's moved by gravity is considered mass wasting. As you already know, we have mechanical weathering and we have chemical weathering. Mechanical or physical weathering is primarily going to be breaking things into smaller pieces. So the first one here is frost wedging. In the case of frost wedging, there's a special property of water that allows it to expand when it freezes. So when water seeps into the cracks of rocks and then it freezes, it pries the rocks open just a little bit. And by that repeated action of melting and freezing of water, we can slowly pry apart rocks. And I know I use the same illustration here, but salt wedging really is the same process as frost wedging. In the case of salt crystal growth, you have salt water that infiltrates rocks. The salt crystals form, and the growth of the salt crystal is going to pry apart the rocks. So I think it's okay to cheat and use the same illustration here. While salt crystal growth and frost wedging tend to occur on very small scales, but over big areas, the mechanical form of weathering known as sheeting occurs on very large rocks. Specifically, it results from unloading or removing the pressure on large bodies of igneous rocks. Igneous rocks that form deep within the earth are under a lot of pressure, especially confining pressure. But it's at those pressures where the rock is considered stable. Now, when you remove that pressure by erosion, you strip off all the overlying rock, you remove that pressure, and the rock then starts to expand. That expansion of rock is going to result in the process of sheeting. So rocks are going to spall off of a giant igneous body in layers like layers of an onion. The result is going to be an exfoliation dome. Biological activity kind of straddles the line between mechanical weathering and chemical weathering. So your book listed under mechanical weathering. And certainly we know that tree roots can break open rocks. Animals can move through the dirt and create trails. Lichens and other plants can physically break apart rocks. But at the same time, if you have biological activity, you're probably introducing water and other chemicals into that system that can further break the rock down by chemical activity. And even though I'm only talking about the overlap within this one particular slide, the reality is that all forms of weathering are going to enhance all other forms of weathering. Now, there are two types of mechanical weathering that your book does not mention, but I wanted to point out. Thermal expansion is probably not nearly as important as the other types of mechanical weathering. In this case, a rock is expanded as it heats up, and it contracts when it cools down. And this doesn't happen over a short period of time. It has to happen over years, many seasons. If you look at cement sidewalks, you've probably seen the same thing. Some of the cracks within sidewalks are because that concrete or the cement will expand and contract over the years. In fact, that's part of the reason why there are often grooves within sidewalks to accommodate that expansion and contraction. In the case of this particular rock on the screen, everything still seems to be in place and nothing's been moved quite yet. So in this case, the breaking was probably the result of thermal expansion. Another way to physically tear apart rocks is by abrasion. And you have some abrasion when rocks in a stream bounce along and they hit each other, or they grind across the bottom of that stream bed. More notable cases of abrasion are going to occur when you have glaciers, masses of ice, pick up stones, and then grind those stones across the Earth's surface. So these grooves that you see here are from a mountainous glacier in South America that cut across the surface. As we move into chemical weathering, essentially everything that's happening with chemical weathering is related to water. So water is going to be key here. It's key because it allows the transportation of ions, transportation of molecules, and that's important because it allows us to break down minerals that are relatively unstable at the surface into forms that are more stable at the surface. So if you took a rock such as a granite and you started to break it down, you would need to have water to truly have chemical weathering and have it break down into the stable components. When you break down essentially any rock into the stable components, the result tends to be quartz, clay minerals, iron oxides, and then ions that are free within solution. Now, how fast weathering occurs depends on a couple things. One is surface area. So if you break things into smaller pieces, there's more surface area. In other words, mechanical weathering can facilitate chemical weathering. There's more surface area for water to act. The rates of weathering will also be determined by the climate in a particular area. If you have temperature swings from cold to warm, that's going to speed up the rate of weathering. If you have a lot of moisture in the area, that's going to speed up the rates of weathering. Your book also talks about rock characteristics in determining the rate of weathering. Well, it's not really the characteristics of the rock. Instead, it's actually the characteristics of the minerals that make up the rocks. So you already know that there are two major categories of minerals: non-silicate minerals and silicate minerals. For the non-silicate minerals, the rate of weathering is determined by how soluble it is. In the case of something like rock salt, the mineral halite, you can put it in your mouth and it's going to dissolve on your tongue. So minerals like halite are going to weather very quickly because they're very soluble. In the case of silicate minerals, it's that silica tetrahedra arrangement. It's the molecular arrangement at the atomic level that determines how fast the silicate mineral is going to weather. And if you look at, essentially, this is the Bowen's reaction series yet again, although it's not labeled as such. The minerals at the top have the higher melting points. They also have the simplest arrangement of silica tetrahedra. At the very bottom, you have the most complex arrangements of silica tetrahedra. So it's the ones on the bottom that are going to be the most resistant to weathering. If you have all the minerals shown here in a pile, it's that olivine, pyroxene, and calcium feldspar that's going to chemically weather the fastest. Quartz is going to be the most resistant and essentially is unsusceptible to chemical weathering. Now, once you start to break things down, we can then mix it with air and mix it with water and mix it with organic material and create something that truly supports life. So at this point, we're creating a soil. The 25% air and 25% water segments of this pie diagram are going to be in constant flux. That 5% organic matter is coming from the leaves that fall off the trees. It's the worms that live in the soil. It's the dead squirrels. Okay. So any kind of living or dead organic material is going to be that small slice of soil. There's a few things that control soil formation, and keep these in mind when we talk about soil erosion in just a minute. So the parent material is whatever the rock in the area is before it's weathered, before it's broken down to create part of the regolith. The time is also important for developing soil. If an area has not been stable for a long period of time, a deep soil profile would not have developed. Climate is also key. If you have a very arid area, you do not develop a deep soil profile. You need to have fluctuations in temperature, and you also need to have a lot of moisture. Plants and animals are not only going to be part of the soil, part of that organic material, but they also contribute by disturbing the soil and mixing the soil. And finally, topography. Topography refers to the shape of the land surface. If you have a steep incline, the material is simply going to run off that slope instead of staying on there to develop into a soil profile. So I've mentioned that phrase soil profile a few times now. This is the general soil profile, and each of the layers are named with a single letter. So O at the top. The O horizon refers to the organic material. That's where most of the organic stuff is. The A horizon is going to be just under that, and it tends to be far thicker than the O horizon. The A horizon is the only other layer that has any organic material, but it's still mostly mineral material. The E layer is also known as a zone of eluviation. Now, this zone tends to be very light in color because water that enters the soil is going to pass through the O horizon and the A horizon. As it passes through, it's going to pick up what's called humic acid. Humic acid comes from humus, which is that decaying organic material. So it picks up humic acid, and by the time it gets to that E layer, that acid reacts with the minerals and removes some of those minerals, removes some of the ions, and then deposits them below in the B horizon. So we have the deposition of ions and the deposition of some of the fine-grained particles within that B horizon, also known as the zone of accumulation. Below that is the C horizon, and at this point you rarely have water seeping all the way down that far. The C horizon is going to be rocky material. It's the parent material that has only been partially broken down. Now, just because you have this general soil profile, you should not expect all soil profiles to look the same. In some areas, you do not have all these layers. In some areas, the thickness can vary tremendously, from a matter of less than an inch to 100 feet. And it's that variation in soils that has led to a soil taxonomy. Taxonomy is a term that just means putting names on something. And so the soil taxonomy system puts names on soils. The soils are given their name based on their characteristics. How thick are these different horizons within the soil profile? What is the composition of the materials within that soil profile? How much time has a soil profile been able to develop over? So now that we've created a soil, let's break it down. The soil erosion is going to depend on what that soil is made out of. So what was the parent material? What are the other materials that comprise that soil profile, including which of the horizons are present? Climate again, slope again, and biological composition yet again. So you'll notice that a lot of the same factors that played into soil formation are also playing into soil erosion. If you have a climate where there are intense storm events, there's flooding events, that's going to strip away soil. If you have a steep slope, or if a slope increases over time, that's going to increase the rate of soil erosion. And finally, if you remove vegetation that's holding the soil in place, soil can be washed away far easier. Now let's move into the section for mass wasting. And again, I would classify this as a type of erosion. It's simply the movement of material that happens to be moved by the force of gravity. In the case of mass wasting, this essentially has to follow weathering. You have to break down material before you can start to move it. There are a number of controls and triggers that allow mass wasting to occur. If you have a steeper slope, you're more likely to have mass wasting. However, there's no minimum angle required for mass wasting in general. It can be a relatively flat surface, but as long as it's not perfectly flat, then gravity can still have an impact. So there's no minimum angle required. However, if you do have steep angles, that's when you can have the most dramatic mass wasting events. All of mass wasting, and in fact all of erosion, is going to result in lowering the land surface. So again, we're just tearing things down. In the case of a lot of mass wasting events, the presence of abundant water is going to be important to allow that event to happen. If you have loose sediment, whether it's sand size or boulder size, and you're on a slope that is not very steep, you have a lot of contact between those particles. And those particles are going to have friction with other particles and generally stay in place. If you add a little bit of water, that doesn't always do much. In fact, in some cases, it can increase the friction. But if you add a lot of water, if you saturate that area, the water forces itself between particles. At that point, this material starts to act as a fluid as opposed to dry sediment. A couple other controls or triggers of mass wasting events are going to be removing vegetation and then the presence of earthquakes to give it a little extra nudge. Now, mass wasting events can be classified by three different parameters: type of motion, the velocity of the movement, and then a third one that your book doesn't mention, which is the type of material. Now, even though it doesn't classify that as another way to sort mass wasting events, it does discuss the type of material. So the type of motion is going to be a fall, a slide, or a flow. In the case of a fall, you have to have very steep areas, and essentially the material is moving through air. In the case of a slide, and the first two top images are types of slides, slumps and rock slides, you have the motion of material along a discrete plane. So there is a well-defined surface on which things are happening. In the case of a flow, such as the bottom two, there is not necessarily a discrete surface, and everything is behaving like a fluid. When we start looking at how fast mass wasting events are happening, they can be classified as fast or rapid versus slow. Now, when I say rapid, and when your book says rapid mass wasting events, some of them will be dramatic, like an avalanche. Others are going to be really, really boring to watch. In the case of a slump, you have material that is moving along a curved surface, and this can occur over days. So you could set up a chair and watch this happen, but you're going to be really bored. In the case of a rock slide, it's also a type of slide, but it's occurring usually quicker. The main difference between a rock slide and a slump is that it's the material. A rock slide is rocks, slump is going to be often soil, but it can be any smaller particles. Debris flows, also called mud flows, it's going to be any kind of material, but almost always soil. And the key thing is that there has to be lots of water. And so this is not the same as having a flooded area, because in addition to water, you have all the sediment. That creates more viscosity. It gives the debris flow more power than a flood by itself. Earth flow is going to be similar to a debris flow, except that a debris flow tends to occur in very dry areas, whereas an earth flow has to occur in very wet areas. So a debris flow occurs normally because you have a sudden rainfall event, and the abundant loose material that's already in the area gets swept up along with that water. In the case of an earth flow, this tends to be far less devastating, but it's in areas that stay wet over long periods of time. Now we can move on to the slow methods of mass wasting. Creep refers to the very slow movement of soil and dominantly the regolith, rocky material, downhill. And this can be aided by the expansion and contraction of minerals due to temperature. It can be aided by water in some cases. So at this point, you may have some difficulty separating out some of these kinds of mass wasting events. Earth flow is nothing that you really want to watch because, again, it's going to be a very boring kind of mass wasting event, but you can watch it happen. Creep is typically occurring over years or decades or centuries, so it's going to be far too slow to watch. In the case of earth flow, I mentioned it's commonly soil, so very small particles, clay and silt-sized particles. With creep, it's any size particles, including very large boulders. In the case of earth flow, you have to have water and the material must be saturated with that water. In the case of creep, sometimes there's water, but not always. Now, one thing we can do is identify when creep has happened. So even though it's too slow to watch, we can see the impacts. So here are a couple different examples. The tree trunks tend to be curved. That's because the soil that's containing that tree has been moving downhill. But trees will try to correct themselves and grow up toward the sunlight. Fence lines, retaining walls tend to be broken and tilted, and roadways can have cracks formed. Solid function is listed separately within your textbook, but it's really a type of creep. Specifically, it's a type of creep that occurs over a dense, hard layer that does not allow water to penetrate any deeper. So because of that, it's going to allow the soil to move very slowly in small little lobes. Now, this is most common in areas that are underlain by permafrost. In the case of permafrost, you have ground that's permanently frozen, so water cannot infiltrate and simply stays in the topmost layer of soil.